Okay, so we talked about being inside the belt of stability in the last video, and we said that nuclei outside of the belt of stability tend to be unstable, and they're going to undergo a spontaneous emission of particles or photons or something. And we talked about the main types of radiation being alpha particles, beta particles, gamma rays, positrons, and electron capture. Now, that first step where that species gives off an alpha particle or a beta particle or a positron or gamma rays or electron capture, that first reaction, which we call a disintegration, okay? So the first disintegration of a radioactive particle or a radioactive nucleus is the beginning of a radioactive decay series. Which is a sequence of reactions that ultimately give a stable isotope. So this is a series of reactions or a sequence of reactions that ultimately give a stable nucleus. So it's not like, so taking a look at that belt of stability, it's not like you're going to give off one isotope, or you're not going to give off one proton or one electron or one positron, and then you become stable. Oh no. So this usually is like you do this over years or sometimes billions of years. So for instance, here's the uranium decay series. So in the first step, and I'm going to mark this right here, in the first step you got uranium-238, and it gives off an alpha particle, but in order for this reaction to go, you need 4.51 times 10 to the 9th years to make. So we're talking about 4.5 billion years in order for a nucleus to break down, to emit an alpha particle, and to break down to give us thorium-234. Okay, then the second step, where you release a beta particle, that's a lot shorter, only 24.1 days. Okay, but then that gives you your third isotope, which then it also gives off a beta particle in only a minute. So that's way fast, but that gives you uranium-234, where the next reaction takes almost 20,000 years in order to give you your next isotope. So after you go through a series of reactions, where the reactions could take thousands of years or only a couple minutes, eventually you get to a stable isotope, lead-206. Okay, so this again, this is your end game. This is your stable isotope. Now, are all decay series this complicated or takes this long? No, but this is for uranium-238. This is one of the more famous or the most studied decay series. Okay, now before we go on, just a little bit of the lingo that we've got to nail down. So the beginning radioactive isotope. In this case, looking at the decay series that uses uranium-238, we call that the parent isotope. The resulting isotopes after uranium-238 we call these daughter isotopes. All right, now we can actually measure the rate of decay at a certain time t by using the following equation. The rate of decay at time t is going to be equal to lambda times capital N. Now, lambda is the first order rate constant, and capital N is the number of radioactive nuclei present at time t. Wait a minute, didn't we talk about half-lives way back in chapter 14? Hell yes, this is exactly what we're talking about. So remember that back in chapter 14, we said that the half-life of a radioactive nucleus is the time it takes for one half of the nuclei to decay in a sample. And we calculated that half-life for a first-order reaction. The half-life was going to be equal to 0.693 divided by the rate constant, K. Okay? In this case, because we're talking about nuclear isotopes, and we've got this lambda symbol instead of talking about rate constants, we would say that the half-life would be measured as 0.693, or the natural log of 2, divided by lambda. So again, this is your first order half-life. Which is awesome, because we talked about this a long time ago. So that means the half-lives of radioactive isotopes will be very different from isotope to isotope. And once you know the decay constant, okay, which is this lambda thing again, this is also the rate constant, you can determine the fraction of radioactive nuclei that remain after a given period of time by this equation, that the natural log of the number of radioactive nuclei at time t divided by the initial number of radioactive nuclei is equal to negative lambda, which is the decay constant, times t, which again, this is the first order integrated rate law. How about that? That's pretty cool. Where n sub 0, this is the original amount, n sub t, this is the amount that's left. T is the amount of time that we're given. Lambda is going to be your rate decay, your decay constant. All right. So let's see if we remember how to do some problems. So here's our first problem. The decay constant for the beta decay of technetium-99 was 1.0 times 10 to the minus 13 seconds to the minus first power. What is the half-life of this isotope in years? Okay, so again, half-life is equal to 0.693 divided by lambda. Now, we know lambda is 1.0 times 10 to the minus 13 seconds to the minus first. So if we pop that in, 0.693 divided by the lambda value, 1.0 times 10 to the minus 13th, seconds to the minus first, this gives you 6.9 times 10 to the 12th seconds. And so that's the half-life for that reaction. All right, here's our next one. Phosphorus-32 is a radioactive isotope with a half-life of 14.3 days. A biochemist has a vial containing a compound of P32. If the compound is used in an experiment 5.5 days after the compound was prepared, what fraction of the radioactive isotope present remains? Suppose the sample in the vial originally contained 0.28 grams of P32. How many grams remain after 5.5 days? All right, so essentially, this is asking us two questions. And the first question that we're trying to figure out is how much P32 is left after 5.5 days. Okay. After we know that, the second question is how much P32 is left. And we're looking for a mass. So that's essentially what we're going to try to solve for. So we're going to deal with number one first. Okay. So the half-life, if you remember, half-life is going to be 0.693 divided by lambda. Okay. All right. Now, if we rearrange this equation and solve for lambda, because we need that, if we multiply both sides by lambda, okay, so half-life times lambda is equal to 0.693, and we divide both sides by half-life, we get that lambda is going to be equal to 0.693 divided by T1/2. So now, if we remember that you have the integrated first rate law that says that the natural log of the amount of radioactive nuclei divided by the initial amount of radioactive nuclei, this is equal to negative lambda times T. We just solve for lambda. So what we're going to do is replace lambda in the integrated rate law with that expression 0.693 divided by half-life. So we get this. Natural log of nt over n sub 0 is going to be equal to negative 0.693 divided by T1/2 times T. Okay. Now, we know that we have the half-life is 14.3 days. Okay, and the T that we're interested in is 5.5 days. Okay, so if I pop those values in, so we have the natural log of nt over n0 is equal to negative 0.693 divided by the half-life, which was 14.3 days, times the time, which is 5.5 days. The units cancel out, so we're going to be given a fraction. So we get that the natural log of nt over n0, that should be equal to negative 0.693 divided by 14.3 times 5.5. That should give us a value of negative 0.267. Okay, now to get that fraction by itself, I gotta make both sides be the exponent of e. Okay, and so if we undo that, we get the fraction nt over n0 by itself. This would be equal to e raised to the negative 0.267, or we should get a positive 0.77. So this is the fraction. This is how much is left. Okay. So that's the fraction. Now, if we're told, the second question was this, we know that we have a mass of 0.28 grams. How much is remaining? So if we take that 0.28 grams and multiply it by that percentage, 0.77, we should have 0.21 grams. And this is how many grams remain after 5.5 days. Pretty cool. So doing these problems, even though they're the wording's a little bit different, it's still the same way that we solve problems back using the integrated rate law back in chapter 14. Now, the half-lives of radioactive isotopes have been used as clocks to determine the ages of certain objects. And right now, there's 3 types of dating techniques out there: carbon-14, uranium-238, and then potassium-40. And carbon-14 is used primarily to determine the relative age of living items like plants or animals. Uranium-238 is used to determine the age of rocks in the earth and also extraterrestrial objects. And then potassium-40 is used to determine the age of minerals. So we can do different types of radioactive dating depending on the materials that we're dealing with.